Hello everyone, we are presenting our blockchain simulator, which can simulate different attacks like a double spending attack or a float attack on a Bitcoin network. First, what is Bitcoin? Bitcoin is a digital peer-to-peer cryptocurrency solving the double spending problem for the first time. Our blockchain simulator is called Vibes. It is capable of conducting large-scale blockchain simulations. The main goal of Vibes is to derive empirical insights on the behavior of the system under attack, and to examine the effects of changes to configuration parameters on the Bitcoin network. The Vibes architecture has two parts. In the first part, the front end, the user can change the configuration parameters. The front end uses the React JavaScript framework and atomic design to easily add or remove components. The back end, the simulator, receives the configuration parameters from the front end. The backend is written in the Scala programming language and uses the Akka framework and the actor model. The main object saves the configuration in the vconf and starts the coordinator. The coordinator is the central piece of the simulator. It allows the node to do work requests. Work requests are, for example, the mining of a block or the sending of a transaction. VBlock is a data structure for a block, and VTransaction is a data structure containing all the necessary information of a transaction. The node repo actor is used to offload work from the coordinator. The coordinator is the bottleneck in the system. The simulation ends after the coordinator realizes that the current timestamp of the simulation is higher than the end timestamp. Then the reducer actor summarizes the results and presents them to the user via the front end. Let's talk about the attacks. A double spending attack is an attempt to spend the same Bitcoin twice and belongs to the family of the alternative history attacks. The illustration shows an example of a successful double spending attack. The attacker's transactions were accepted in a block A. This block A is shown in the second tree as the yellow valid block above the white block. The attacker wants to make these transactions in the yellow block invalid. So he starts mining on his own branch with the white block, which contains transactions contradicting the other transactions. Now the attacker can mine in secret until the victim has accepted the transactions. For example, in Bitcoin it is recommended to wait for 6 confirmations to be sure about the finality of the transactions. After the victim accepted the transactions, the victim does something beneficial for the attacker. Then the attacker can release his own branch, which needs to be longer than the honest official branch. Now the longer blockchain mined by the attacker is accepted by everyone, and the transactions in block A are no longer valid. The success probability depends on the malicious miner's hash rate and the number of confirmations. Let's talk about the float attack. A float attack attempts to make everyone in the network to pay at least a certain target transaction fee by generating lots of valid transactions. In the illustration, the red nodes would send these transactions. In the transaction pool, the transactions are ordered by transaction fee per size by the miners to achieve the highest financial return. If there are only nodes incentivized by financial return, then the transaction with the lowest fees below the target transaction fee are crowded out. This means they are not going to be included in any block. Let's take a look at the simulation configuration parameters. There are 17 of them. You can only see 16. The 17th is the strategy, which means you can either choose between a generic or a Bitcoin blockchain simulation. For now, only one double spending attack or one float attack can be simulated within one simulation. The simulation results show a successful double spending attack. The important configuration parameters are that the attacker's percentage of the total hash rate in this scenario is 40% and that the merchants wait for 2 confirmations. The theoretical probability of a successful attack is about 70% in this case. And in this simulation the attack was successful. Another interesting metric is the maximal safe transaction value, which is 21 Bitcoin in this scenario. This means it would be profitable for an attacker to do a double spending attack if a merchant accepts a transaction with a higher value. The following section shows the two most interesting and important graphs about the float attack. In this case, we can say that the float attack was successful since no transactions with fees below the target transaction fee were confirmed in any blocks. As you can see in both graphs, the target transaction fee was 30 Satoshi. The first graph shows that no transaction below 30 Satoshi were confirmed and that all transactions with more than 30 Satoshi were accepted. The most transactions have a transaction fee of exactly 30 Satoshi. Most of these transactions are one of the 787 transactions generated by the attacker. A participant of this network would choose any transaction fee above 30 Satoshi to get his transaction confirmed, or maybe exactly 30 Satoshi if the participant is willing to wait a bit. This waiting time is shown in the second graph. Since no transaction with fees below 30 Satoshi were confirmed, the average confirmation time for these transactions is 0. The average waiting time for all the confirmed transactions is about 1 block, except for the transactions with 30 Satoshi, which need to wait for about 3.5 blocks. In the end, we want to show you the full result page of our front end. Here you can see even more information than we can show on the poster. For example, here is geographical information or the time between blocks, information about transaction, about SegWit and non-SegWit. Thank you very much for your attention. If you're interested in our research, please contact us or check out our GitHub repository. Thank you.